Hello, IB. We're starting off with Chapter 18, and we're just looking at 8.1, which is the area under the curve. And we actually discussed this in class the other day, just thinking about how you would actually find the area that's underneath a curve, so not a straight line. And we talked about Riemann sums and how if we could just divide it into some rectangles, we could possibly get a good approximation, because you could take rectangles that are over the curve, so you get a little extra area. And we could take rectangles that are under the curve, so now we're missing out on that same area, or similar area. And that way, when you guys are actually infinitely taking more and more and more rectangles and adding up those areas, you wind up converging toward the actual area. So we discussed how the area of the lower sums is less than the actual area, but that's sandwiched between the area of the upper sums. So we can use this to approximate. It's not going to be the most effective method, but it is a really good method to just kind of understand the basics of where this area is coming from. So for example, if we were graphing 1 over x, so this is y equals 1 over x, and we're asked to divide it into 6 strips of equal width. So we went ahead and made 6 separate strips. So 1, 2, 3, it's 1, 2, 3, 4, 5, and 6, and they're between x value of 2 to x value of 4. So if we want to figure out how wide each of these rectangles is, so the width, we would take 4 minus 2 and then divide by 6. So basically our width is 2/6 or 1/3. So that means every one of these rectangles is 1/3 units wide. So if we wanted to actually label our x-axis, we would have to add 1/3 every time. So if we start at 2, this would now be 2 1/3 for that next x value, or 2 2/3. 2 3/3 would just be 3, and then we have 3 1/3, and 3 2/3, and then 3 3/3 would be 4. So those are our 6 separate divisions. Now when I'm actually looking at finding the area, I can actually look at one separate rectangle. I know that the width is 1/3 for all of these rectangles, but now the height is what I need to use the function for. So if I notice this first rectangle, if I'm talking about the upper rectangle, it's going to hit the curve at a height that's equal to that y value. So if I want to find that y value, I would have to substitute the corresponding x value into my function. So this first point has a y value when x is 2, so therefore this height would be 1 over 2, or 1/2. So that would be the height of this rectangle. And then that pattern would continue. If I look at my second height, this has an x value of 2 1/3, which would be 7/3. So 1 over 7/3 would be 3/7. And then I could continue to find the heights. Again, if I'm doing the upper rectangles, I have to keep looking at this left corner of the rectangle. And if I were doing the lower rectangles, I would use, let's say, green for that one. Then I would suddenly be looking at the right corner, because the top of this rectangle hits the graph at this right corner. So I would start at 3/7 as my y value, and then that would continue as I go. So we did a few of these in class the other day, and just to reiterate how we actually find the area of these rectangles, you guys are welcome to try both of those, and we can check this one in class, but just want to get it set up for you. So what we're actually moving towards is something called the definite integral. So looking at this with a little bit more of a formal approach. If you all are taking any function, so y equals f of x, and it is a positive function, which means your y values are all above 0, and it's increasing, so your derivative is also going to be positive, right? Think about what these different things mean. And you're cutting it off between x equals 0, a to b. So x is greater than or equal to a, but less than or equal to b. So our x values are between these borders of a and b. That means if we call our first x value x sub 0, and our second x value x sub 1 and x sub 2, and so on and so forth, we would get all the way up to x sub n. All of these values, depending on whether we're doing the lower or the upper rectangles, are the x values that we would substitute into our function to find the corresponding y values for the heights of our rectangles. To find the width of each of these rectangles, it's always b minus a divided by how many subdivisions you have. So right here, this is what we've been using to find the width of our rectangles. And then the height of the rectangles is dependent on whether we're doing the lower rectangles or the upper rectangles. So if we take a look in more general terms, this is just some function. We're not sure what the actual function is, but you have the area of your lower rectangle. So you always have the width multiplied by the height. So the width being b minus a divided by n, and the height being dependent on the function evaluated at that corresponding x value. So at x sub 0, that's our first x value, substituted into our function because it hits directly at that point. The second height, so again, width times height, will be dependent on x sub 1 and then x sub 2. But notice we only go up to x sub n minus 1. So we never actually will substitute in that last x value when you have rectangles under the curve, because we're not actually hitting the curve at that last x value. So we only go up to x sub n minus 1. So what we're saying is we're multiplying all the different heights by the width. So the sum of all the various heights, if we factor out the width, so factor out the width, and then we have the sum of all of our heights when you start at the first iteration, which is x sub 0, and then our last one at n minus 1. We also noticed in class the other day when we did our upper rectangles, it was the same pattern, width times height, but we started with the right corner or the opposite corner, depending on whether the graph is concave up or concave down. And that's just looking at the top of the rectangle and noticing where it hits the curve. So this first rectangle hits the curve in the top right corner. So I would sub in x sub 1 as my first x value to find my corresponding height. And this time I would actually go all the way to n. So that last value, b, which is x sub n. And I would evaluate it at that last x value in my interval. So if you notice that pattern, we start with x sub 1, and we'll go all the way up to x sub n. So again, if you factor out your width, it's the width multiplied by the sum of all of your heights. So the first iteration starts at x sub 1 and goes all the way up to n. Now remember, we're trying to find the actual area. So we're trying to figure out, well, if this converges to what in between the lower and the upper area sum. So what's the difference between the two? So if I actually subtracted your upper area minus your lower area, notice everything is in common except for the first and the last terms. So if I wound up subtracting the area of the upper minus the area of the lower, everything would cancel out because it would be the width times the function value at x sub 1, which would cancel out with this one, and then x sub 2 and x sub 3, all of them would cancel out, even the x sub n minus 1, except for that last term evaluated at x sub n, and this first term evaluated at x sub 0. So you'd wind up with your width, which is really b minus a over n, that's your width, and then the f of b minus the f of a. So b being the last iteration, the last x value, and then f of a being the first one. Okay, so notice that this is the pattern that we wind up finding, and we're going to take a look at this in class as well. We also discussed that as your subdivisions increases, so if we took the limit as n went to infinity, remember n is how many divisions you have, of that difference, the difference should get so small that it should be insignificant, because if your n winds up going to infinity, which is your denominator here, this whole part would go to, this whole fraction, which is what you're looking at, would really be going to 0, because your denominator will continue to get larger and larger and larger. Which means if that difference goes to 0, then you're going to get closer and closer to your actual area. Again, this just reinforces that your area of what that space is that we're trying to find is sandwiched between that lower and upper area. So again, you have a limit as n approaches infinity, and you converge to the actual area. In summary, what we're looking at is what's called your definite integral. So a little bit of the notation, just reinforcing now again from class, is that you're taking the definite integral of some function f of x, starting from a and ending at b. That's how you would say it out loud. So this notation says, to find the area under the curve, we take the integral from a to b of our function f of x, and this piece we say with respect to x. So we're giving x respect because you're taking the antiderivative, or you will be taking the antiderivative, which is your integral here, with respect to what your input value is, which is x. So your function is with respect to x, so you take the integral with respect to x as well. All right, so that one is 2x with respect to x. So if your function is greater than or equal to 0 for all values between a and b, which is what we have here, then your integral is going to equal the area. So think about what happens if our function doesn't just stay above the x-axis. So when we first started this discussion, we were taking a look at what would happen, if there we go. So this one, your function is greater than, I guess it technically could be equal to 0. But if it dips down below, then think about what's going to happen to that area. And if I added up all the areas of those rectangles, what would wind up happening? Because that'll be part of our discussion down the road as well. So again, this is our example. If we have a function ax squared plus x, we'll take the integral with respect to x. We could also take the integral with respect to a, but then we'd be treating your x's as constants or some kind of number. So you'd be treating them as a number instead of as a pronumeral. All right, guys, so just taking a look at number 2 from 18A2. If you're asked to sketch this graph, of course, we would wind up, we could sketch it by hand, or just to get a good picture, and take it to our calculator, and we've got square root of 1 plus x cubed. I set my window at a little larger than the actual interval they wanted us to go at because of what we're going to do next with it. So I went from -2 to 4, but we're interested more from 2 to 4, I believe. Sorry, 0 to 2. Write an expression for the lower and upper rectangle sums using n subintervals. So again, we're looking at, okay, 0 is going to be our a value, 2 is our b value. To find the width, it's b minus a over your subdivision. So this would be 2 minus 0. And we are using, okay, it could be 50 subdivisions, 100 subdivisions, 500 subdivisions, so just divided by n. And again, we can get a pretty good approximation by saying for the lower rectangles, our width multiplied by the sum of all of our function values evaluated from 1 to n minus 1 for the lower, and then going from, so that could be something like 0 to 499 if I were doing 500. Okay, that would be our best approximation because it's going to say find the lower and upper rectangle sums when n is 50, 100, or 500. Well, our best estimate is going to be using that 500. And then, of course, we'll shift everything when we do the upper. So the upper would be going exactly from 1 to 500, where the lower would have been from 0 to 499, which is your first iteration to your last iteration. Okay. Now, the way that we are going to do this, I have my graph on the calculator, but you guys, of course, will not be doing 50, 100, and 500 subdivisions by hand. So this is how well can you use your technology. And you guys actually were introduced to a couple things the other day. One of them being on our iLearn page, you guys have a link now to a GeoGebra site, and you guys can actually type in the function. This is the same program that's on your CD that comes with your textbook. So you guys are able to type in the function right here. So you could type in the square root of 1 plus x cubed. You can also change how many subdivisions we have. So right now it's set to 50, but I can actually change that as well. And then I can get a pretty good approximation for what I actually am able to find here. There's a similar program that's in your textbook, and you guys can click on the link from your textbook to do the same exact idea, to find your sum using lower and upper rectangles. If you guys are in your calculator, the other way you guys can use the technology is by going to Menu and, Analyze, and you guys have an integral option, and it automatically will ask you where you'd like to start. So I'm going to go from 0. And I'm going to come out to exactly 2. Now, if you type in 2, hopefully that will take you directly there. Oh. Figure out, there we go. I think your calculator is a little different than mine. There we go. So it'll give you a pretty good approximation of what your area actually is. Did it take it? Oh, it did originally. Excuse me. There we go. So either way, again, that is under Menu and Analyze and Integral. Okay, so we go from 0, again, that's your lower bound, up to, I'm going to type in 2. That'll automatically take me to 2, and then it spits out what your actual area is. All right, so if you guys want to play with those two, because we are going to use those a little bit more throughout the rest of the chapter. To leave you guys with a little bit of work tonight, to start our discussion next class, there are 3 separate functions here. So y equals f, y equals x, and y equals 2x plus 1. Okay, or this function is equal to 5, this function is equal to x, and this function is equal to 2x plus 1. So what I'd like you guys to be thinking about, based off of our discussion this first introduction day to integration, is if your function is f of x equals 5, and I'm going to try to find the area under the curve between a and b. We don't know what those values are, so we're just going to leave them a generic a and b. How would I write an expression for finding the area of that space? Because it is an area of a shape that we are very familiar with. Same thing for the second one, when function is x between a and b, and the same thing for the third one. So try to come up with an expression, and we're looking for a pattern in how these expressions are being created. All right, and we'll start our discussion with that next time. Have a fabulous night. See you guys tomorrow.